All right. So we are looking at the last part. This is basically for A-level mathematics, where we are actually using our integration techniques to solve differential equations. In any case, in most cases, when we're doing differentiation, we never probably mention the term differential equation, but anything that has got an equal sign, um, an algebraic statement that has an equal sign is an equation. So any algebraic equation that has got derivatives and equal sign is definitely called a differential equation. So we're creating differential equations in differentiation. Now we can solve them. Obviously, to solve a differential equation goes without saying we should be using integration, because we have found out that differentiation and integration are inverse processes. So we simply basically use the reverse differentiation process term here to solve um, differential equations. So we are going to restrict our solutions only to first order. There are quite a number of techniques you can think of, because we've got first order differential equations that requires separation of variables, which is basically collecting, grouping, which is basically grouping like terms here, grouping like terms. We do have other linear first order differential equations that cannot be used, that cannot fit into this category of separating variables. Might want to use the integrating factor. We do have second order and higher orders that requires other techniques, substitution, which is the Bernoulli equations and Riccati equations. There are quite a number of techniques that you could do as you grow up with mathematics to higher levels. So far, we're going to look at only one term, which is separating variables. So the type of equations you are most likely going to face are those equations that have got a dy and a function, or a product of a function that is in terms of x and y, and it is easily manipulated into um, y and x on their own, which is grouping the terms, and we just said we have separated the variables. And eventually, when you solve a function of that nature, you create a family of solutions. It is like, say, for example, working from the answer, working backwards. If I know that y squared, y is equal to x squared, I know that dy over dx certainly is 2x. However, if this is not given, you're just given dy over dx is equal to 2x. Then you need to go back to y squared is equal to x squared. You simply need to separate these variables. And first of all, what you do is you're going to say both sides dy is equal to 2x dx, and you apply the integral signs. You get y is equal to x squared plus c. Then, in order for you to go back here, you would have been given initial conditions that x is 0 and y is 0. Then you know that the function is actually y is equal to x squared. However, there is, in general, this represents a family of equations that look like this. Depending on what? On the value of c. All right? That's basically what we're saying. So the solution to these differential equations is this, where c is the one that restricts us where we are. In this case, we are here. That's where the value of c is. So let us look at just two examples of how do we apply the separation of variables to solve differential equations. So like I said, any statement that has got an equal sign is an equation. However, if it includes a derivative, it becomes a differential equation. So this is a differential equation, qualifies to be called a differential equation. First order, because the highest power is 1, we have this dy over dx in here. So what are we going to do to solve it? We group the like terms. We separate the variables. That's a mathematical term. So for me, it looks like the easiest way is to divide both sides by 1 over x squared. If I do that, I'm going to have dy over dx is equal to x over 1 plus x squared, then tan y. Normally in an exam we will do this quickly. And I'm going to divide again both sides by tan y. I'm just rearranging. I'm going to have 1 over tan y is equal to dy over dx is equal to x over 1 plus x squared. And finally, the separated variables are 1 over tan y dy is equal to x over 1 plus x squared dx. Now we solve. To solve such a question, we probably need to look at this quotient 1 over tan y. We will probably need to change it and say this is cos y over sin y dy is equal to x over 1 plus x squared dx. Why did we do that? Because we already know a technique that says if we are differentiating or if we are integrating quotients of this nature with a k here, maybe I will have 1 over k natural log of f of x. So this is the technique we know. Integral of this quotient that looks like this. This is a k, is this one, plus c. So if you look at it, this numerator cos y is a derivative of sin y. So if I apply the integral sign here, the answer here is natural log of sin y. And if I look on the right hand side, again, the numerator is x. The denominator is 1 plus x squared. If I differentiate 1 plus x squared, I get 2x. Yet we've got x here, but it's still the same form. So I just need to divide by 2 and say natural log of 1 plus x squared plus c. So technically this is the answer. This is the answer. Anything else that is coming out of this is you applying your integral skills, your integration skill, your exponential skills to reduce it into another form. For example, we know that if we apply the natural log here, we are going to have sin y is actually equal to e. Actually, I don't need to do that anymore because I know if I apply e here, I'm actually going to get, let me just write it, I'm going to get e natural log of 1 plus x squared to the power of half times plus c. That's what I'm going to get here, plus c. And this will be written as sin y is equal to e to the power of c. These two cancel each other, we just get 1 plus x squared to the power of half. So I can actually write it as a square root of 1 plus x squared, where e to the power of c is equal to a. So I can actually reduce this answer to this form. Separation of variables, that's the answer. Alright, let us look at another example. Again, as you can see, it's dy over dx, first order differential equation. Unlike the first one, we actually have the initial conditions that says x is equal to 1 and y is equal to 4. So we are going to leave our answer in the form of y is equal to f of x. So the first thing to do is to separate the variables by just dividing and rearranging here. We get dy over y minus 2 is equal to, just gonna do, I'm doing it by inspection, you divide both sides by y over 2, y is cancelled, is equal to minus 3 over 2x plus 1 x plus 2, multiply both sides dx. So that's the separated form. You could do it step by step, but at this level of mathematics now, there is probably no good reason for you to do that. But if you don't feel comfortable, yes, I would advise you to go through it step by step. Now, what we can see here is before we can integrate, we can apply our integral signs, that's fine. But what we can see is this part here requires us to simplify it. And the only way we can integrate this is to use what we call partial fractions. So we have minus 3, 2x plus 1, x plus 2, which is a over 2x plus 1 plus b over x plus 2. This goes on to become minus 3 is equal to a x plus 2 b 2x plus 1. So if I eliminate a by setting x to minus 2, I'm going to get minus 3, because x is minus 2, I'm eliminating a. I'm going to get minus 3, minus 2 here, that's minus 4 plus that's minus 3b. So this implies that b is actually equal to minus 1. And if I eliminate b by setting x is minus half, clearly you can see that if I put minus half here, these two cancels out, we get minus 1 plus 1, 0, b is gone, minus half here. If I put minus half here, I'm going to be left with minus 3. So minus half plus 2 is simply 3 over 2. Yeah, 3 over 2. So this is going to be 3 over 2 a, not b, sorry, a, which implies that a is equal to minus 2. So in a way, we have a solution, we have a simplified solution of this function, which is identically equal to a being minus 2. So we've got 2x plus 1 and b being equal to minus 1. Hold on a second, I just want to check something here. Minus plus goes. Okay, this was positive from the word go. This was positive. Okay, this was negative. There is a mistake here because this is negative. B is negative here, so we get minus 3. And there is a negative, so this is actually positive. Yes, B is positive. You gotta be very careful with your signs anyway. Plus 1 over x plus 2. So this is exactly what we have here. So we're going to come back to the integral sign. We say this is equal to the integral of 1 over y minus 2 dy is equal to the integral of minus 3. I would rather take the 3 outside the integral sign, or rather, I would rather just say this. Instead of putting this here, I'll put this whole part here. So I'm going to say this is equal to the integral of minus 2 over 2x plus 1 dx plus the integral of 1 over x plus 2 dx. Again, this is the same way. The integral here is natural log of y minus 2. The integral here is just minus natural log of 2x plus 1 plus natural log of x plus 2 plus c as your answer. Okay? And how are you going to put this into a much simplified form is entirely up to you. I would say, I would write it as, well, I can just say this is natural log of y minus 2. This is a minus, so we can apply the rule, which is going to be equal to natural log of x plus 2 over 2x plus 1 plus c. We can eliminate the natural log here. And when we do that, but instead of doing that, we might just want to deal with the initial condition that was supply it. It said x is 1 and y is 4. So we've got a condition that says x is 1 and y is 4. What happens if I do that here? I'm just going to have natural log of 4 minus 2, and x is 1. I'm going to have 1 plus 2, 2 times 1 plus 1 plus c, which is natural log of 2 is equal to natural log of 3 over 3, which is the natural log of 1. 1 plus 1, 1 plus 2, 3, 2 plus 1, 3. So that's the natural log of 1 plus c, which means c is just the natural log of 2. So we are already close to the answer. C is natural log of 2. So we are going to have natural log of y minus 2 is equal to natural log of x plus 2 over 2x plus 1 plus natural log of 2. Again, this reduces. Again, this reduces to natural log of 2 in brackets x plus 2 divided by 2x plus 1. Just apply the exponential law here. Y minus 2, which is y minus 2 is equal to 2x plus 2 over 2x plus 1. This continues by saying y is 2x plus 2 over 2x plus 1 plus 2 is required. Y is equal to f of x. Alright, that's how we solve